Hi everybody, I'm Greg Fishel. Welcome to bonus weather video number 2 for this week. And I'm not sure why in all the time I've been doing this that I never thought to do a video on this particular topic, but it's something that's widely used in weather forecasting and meteorological analysis, and it's very helpful in assessing how air is moving. Air, of course, moves in 3 dimensions. It isn't just north, south, east, west. It also goes up and down. And so this is a tool that is very useful in assessing that, and that's what we're going to be talking about today. So for those of you that haven't seen this before, this is called, and don't worry about reading it, okay? Don't worry about that right now. This is called a skew-T log P chart. It's skew-T because the lines of equal temperature are skewed, and it's log P because the mass in the atmosphere is distributed logarithmically. And I want to demonstrate that now. So these are all lines of constant pressure, okay? Ground's down here, and then you're going up through the atmosphere. This is 1,000 millibars, 900, 800, 700, 600, 500, and 400. Notice that the spacing between these two lines is less than it is up here. It's the same amount of mass, okay? It's 100 millibars of mass, but it occupies a bigger volume. And so that means the air is less dense. So the maximum density of the atmosphere is down near the ground, and then it progressively gets lower as you go up through the atmosphere. So that's why those lines are not spaced equidistantly. All right, so for the purposes of this video, we're just going to concern ourselves with the 1,000 millibar surface, which, if you are relatively near sea level, that's where this surface is going to be. Sometimes it's just above the ground, sometimes it's just slightly under the ground, but basically there. You can't do this, well you can, but like out in the Rockies, if you have an elevation of 10,000 feet, this is sort of meaningless out there, okay? Because you don't really want to look at something that's 2 miles underground. All right, so there's our 1,000 millibar surface. And basically by using something called potential temperature, which is what the 1,000 millibar surface is used for, it normalizes all temperatures to a common level, okay? So let's say that we have an air parcel, which I've denoted here by this little blue square, okay? And it is going to, well, remote control gave me a little fit there. All right, so it is going to move down what we call a dry adiabat. And there are a whole bunch of these adiabat lines that go like this. Now, an adiabatic process is a process where there is no heat exchange with the environment around that air parcel, okay? It can only change temperature by changes in pressure. So that would either mean compression or expansion. But that's the only way it can change if it's an adiabatic process. Now, if you get into a situation where you have condensation going on and there's heat being added to the atmosphere, or evaporation where heat's being taken away, then that is a non-adiabatic process, okay? So that's the difference between those two. So this parcel, if it moves down that dry adiabat to 1,000 millibars, I don't know why this is giving me fits here. Let's see. That was supposed to move. There we go. I don't know. So it moves down the dry adiabat. When it gets to 1,000 millibars, that is the potential temperature, whatever that happens to be. It's pretty warm over there, okay? Now that we know what that is, let's move on and take a look or discuss a few other points here. Okay, a line of constant potential temperature is also referred to as an isentrope, which is a line of constant entropy. And I am not going to get into the definition of entropy because all of our heads will be spinning by the time I get done with that. So it's not really important, but these surfaces are called isentropic surfaces, okay? Air parcels move along isentropic surfaces, not surfaces of constant pressure. The reason when you go into a weather office that you see an 850 millibar map and a 700 millibar map and a 500 millibar map is that the equations in meteorology are simplified if you use constant pressure surfaces. But you can't actually look at an 850 millibar map and say, okay, the wind is from the southwest and it's plus 10 degrees here, C, and up here it's 0, and so that 10 is going to go right toward that 0 because air does not move along surfaces of constant pressure. It moves along isentropes. So that's what I wanted to point out there. And then, maybe I have a bad battery, I don't know, geez. So performing an isentropic analysis in effect combines temperature and pressure into one variable. It simplifies things. And the only case, and I just talked about this, in which air parcels do not follow isentropic surfaces is when heat is exchanged with the environment, such as the warming effects of condensation and the cooling effects of evaporation. Okay, so let's go back to our SKU-T chart here. And here are our pressure lines, okay? Now, potential temperature is going to increase with height. Now, regular temperature normally decreases with height. Potential temperature increases, and I'm going to explain why. So these are the isotherms. These are the skewed T lines, hence the chart being called SKU-T log P. So we've got our isotherms, we have our pressure levels, okay? Now, I'm going to look at 3 different air parcels, one starting up there at 400 millibars. This is really strange. Okay, there's 600 millibars and there's 800 millibars, okay? All right, so this one has farther to travel to get all the way to the ground, right? So its potential temperature is going to be way over here. This one, as it goes down the dry adiabat, its potential temperature is much cooler. And then this one doesn't have far to go at all, and its potential temperature is going to be even cooler still. There we go. Okay, so potential temperature increases with height. Now, what do we do with all that to make use of something in terms of weather forecasting? So, and this, by the way, is courtesy of a website called tropicaltidbits.com. And you may think, what are you doing looking at a tropical website in the middle of winter? Well, the guy that did this website, that constructed it, he's brilliant, okay? And he has so many more things on that website than just tropical meteorology. And one of the things he has is that you can create cross sections, okay? And so what I did was I say, I want to look at a cross section from, let's say around Apalachicola up here to just north of Richmond, okay? And you usually want to orient this in the direction that the upper level winds are blowing, okay? So now let's take a look at what that looks like. So this is Apalachicola over here, and this is just north of Richmond over here, and Raleigh is sitting about there. Now, do you notice the packing of these isentropes here? Like they're sort of a tight ribbon? This is where the dome of shallow cold air is, okay? And I've outlined that here in a transparent blue. So everywhere underneath that steep packing of isentropes is where the shallow cold air is located. And you can see that it sort of tilts down here, and this is where the front is, okay? It can either be a cold front or a warm front. If the cold air is advancing southward, it would be a cold front. If it's retreating, it would be a warm front. But there's the edge of it right in there, okay? And then this area back in here is just uniformly warm. Okay, so now if the winds are blowing along that cross section, notice how those isentropes are not horizontal. They're tilted a little bit, tilted upward, okay? So what's going to happen here is that you're going to get air that is going to be rising over that cold dome, okay? So it's going to approach the front, and then the isentropes are going to be tilted, and it's going to go up and over that. And this is why you have a large area of steady precipitation north of a warm front, because you have gentle ascent, okay? Now, if the air is moist, you can still get some pretty heavy rain or snow or whatever, but basically it's a large-scale ascent that extends over an extended distance, okay? So north of a warm front, you tend to get large areas of what we call stratiform precipitation, where along a cold front, it's much more concentrated, usually right along and ahead of the front and much narrower in existence. So again, this is a way to assess the atmosphere from the side to see how air parcels are going to be moving either up or down, in addition to the east and west stuff. And you can also sometimes see upper level fronts. Believe it or not, those exist. And if you saw an area of tight packing of the isentropes up in here, then that would tell you that there's something going on up there as well that you need to be aware of. So this is pretty interesting stuff, and at least to me anyways. And so I just wanted to share with you one of the tools that are used in forecasting the weather. And there's also a thing in here called frontogenesis, and that can lead to banded precipitation, and maybe I'll do a bonus video on that on Friday, okay? All right, that's it for now. I hope you have a wonderful Wednesday evening, and we will talk to you again tomorrow. And watch out for the rain and the fog tonight. Take care, everybody.